Welcome to this explainer. Imagine this. It's 2 a.m., your pager is absolutely screaming, and production is hard down. Today, we're diving into the high-stakes forensic detective work of solving a live Java production incident using hard evidence, not just guesswork. Now, when those alarms start going off, the absolute worst thing you can do is just blindly try out command line flags or restart services hoping the problem magically disappears. Doing that literally destroys the scene of the crime. Expert Java troubleshooting is entirely evidence-driven. We really have to ask ourselves which runtime signal actually proves the bottleneck.
All right, let's jump right into Section 1, the production incident.
Picture the incident board right in front of us. We've got a system that is just screaming at 100% CPU. Our P99 latency, the experience of our absolute slowest users, is rising rapidly. And yet, the heap is perfectly stable and our thread dumps show threads actively running with no obvious deadlocks. So the system is working incredibly hard, but doing what exactly?
In a high-pressure situation like that, man, it is so tempting to just jump to conclusions, point a finger at the database, and throw a ton of money at scaling it up. The flawed logic always goes, latency is high, threads are busy, so they must be waiting on the database. We have to resist that red herring. Going with an unproven conclusion just wastes time and budget. We need to find the real bottleneck using actual runtime signals.
Which brings us to Section 2, preserving the evidence.
Look, you have got to collect your evidence before someone hits restart and totally ruins the crime scene. If you reboot that server, your proof just vanishes into thin air. So follow these precise steps. Step 1. Capture your process flags in a bounded JDK Flight Recorder, or JFR recording. Think of this as a time-box snapshot of your JVM's behavior. Step 2. Capture several thread dumps using a tool like jcmd. Step 3. Only capture heavy heap information if an out-of-memory error is imminent and you can actually afford the pause it causes. And finally, Step 4. Only restart the process if it is absolutely 100% necessary to restore service.
Moving right along to Section 3, mapping your diagnostic tools.
Think of this next part as your ultimate cheat sheet. You've got to map the incredibly powerful tools the JDK gives us to the specific symptoms you just captured. Notice how we align the tool directly to the forensic target. We use the JDK Flight Recorder for CPU hotspots, allocations, garbage collection, and locks. Thread dumps are specifically for thread states and deadlocks. Heap dumps, strictly for retained memory. Native memory tracking for direct memory or RSS leaks. And finally, class histograms give us a super fast look at object population growth.
So the really crucial takeaway here is matching the right artifact to the symptom. Whatever you do, don't blindly grab a massive heap dump if you're hunting down a CPU spike. Heap dumps are fantastic for retained memory leaks for sure, but they can pause your entire process and they contain highly sensitive customer data. Use thread dumps instead for CPU or hanging issues. And hey, remember to capture several of them over a few seconds, not just one, so you can actually spot persistent blockers or a massive thread explosion.
Now, when you're actually interrogating those thread dumps, you absolutely have to distinguish real, runnable CPU work from threads that are just blocked or waiting. A thread state of runnable means it's executing or waiting in native I/O. Blocked means it's actively trying to acquire a lock to enter a monitor. Waiting means it's waiting indefinitely for another thread to do something, while timed_waiting just means it's sleeping or on a timed wait. Understanding these states lets you instantly spot connection pool limits, deadlock sections, or long stack traces that are just stuck in the exact same code path.
But hey, sometimes the problem isn't even in the standard Java heap at all, right? If your heap looks totally fine but memory is still ballooning, you have some great lightweight options. You can cross-reference class histograms to spot byte arrays, char arrays, strings, or domain objects that are just growing out of control. Or you can use native memory tracking to hunt down direct memory or RSS leaks, which is incredibly useful when a container gets OM killed, but your JVM heap metrics looked perfectly stable the whole time.
All right, let's track down the real culprit in Section 4, finding the real bottleneck.
Since our specific incident involves a massive CPU spike, we are going to turn to the JDK Flight Recorder, or JFR. If you haven't used it, this is a built-in, incredibly low-overhead event recorder right inside the hotspot JVM that basically acts as the ultimate black box for your Java application. It is totally safe to production and captures an unbelievable wealth of data: CPU method profiling, allocation profiles, GC pauses, lock contention, and even file and socket I/O.
When we interrogate that JFR evidence, the very first question we've got to ask is, which methods are actually chewing up all that CPU? We look at the flame graphs and hot method views to see if the CPU hotspot is in our custom application code, hidden away inside framework code, or somewhere else entirely, like crypto, regular expressions, or heavy serialization tasks.
Next up, we ask the JFR allocation view. Which classes are allocating the most bytes? I mean, which stack traces are just absolutely dominating the profile? We really need to figure out if that high allocation rate is tied to a specific API endpoint, a heavy background batch job, or maybe tied directly to our serialization logic. Keep in mind, high allocation rates force the garbage collector to work overtime, which just burns even more CPU.
So by following a methodical, high CPU diagnostic decision tree, we can systematically rule things out. You capture the JFR, check those hot methods. See if garbage collection is stealing all your CPU cycles. Check for lock contention, and analyze the allocation rate. By doing this step by step, we put green or red evidence markers on our theories. We can definitively rule out the database, for example, because we can clearly see the CPU time isn't being spent waiting on SQL latency.
That leads us right into Section 5, fixing and verifying.
And boom, our JFR interrogation finally reveals the true culprit, massive JSON serialization. We're talking immense allocation pressure from repeatedly building these gigantic response objects. The database, completely exonerated. And the beauty of this is that our fix doesn't require any shiny new hardware or a massive infrastructure bill. The corrective action is beautifully simple and contained entirely in the code. We just shrink the response size. We implement response pagination and use smaller data transfer objects, or DTOs, to lighten up that serialization path. We fix the root cause, not just the symptom.
Finally, we close out the case with the verification phase. We check the incident dashboard, relying on the exact same signals we measured during those crucial first 5 minutes. And what do we see? Dramatically lower CPU utilization and allocation rates, and our P99 latency has returned strictly to our target SLA. By preserving the evidence and actually analyzing the artifacts, we proved, beyond a doubt, that our fix worked.
So I'll leave you with this. The next time those alarms go off and production is literally on fire, are you going to preserve the scene and follow the hard evidence using the powerful tools the JDK provides? Or are you just going to guess in the dark? Stick to the data, use your diagnostic tools wisely, and you will find the real bottleneck every single time. Thanks for joining me on this explainer, and happy troubleshooting.